Alright, so this video is to record problem number 3 from the Flex Activity Applications of Quadratic Functions, which resembles number 11 on the test review. So it says a rocket is launched from 150 feet above the ground at time 0. The function that models this situation is given. So that means we should first, of course, type it in our calculator. So I'm going to go to y equals and clear out what I have, and type in negative 16x squared plus 76x plus 150. Now we should understand if a rocket is launched up in the air, it's going to go up, but eventually it's going to come back down. So similar to the first two problems, we know that if we were to sketch a graph of this, with the y-intercept being 150, that I could mark 150 on my y-axis, and that this rocket is being launched from a height of 150, but eventually will come back down and hit the ground. Now, theoretically, we know that parabolas go on forever in a particular direction. In this case, down, because our a value is a negative. So when a is negative, it opens down. When it's positive, it opens up. But I'm only going to have this in bold because it's the only practical part of the graph. And that's going to be important as we talk about the practical domain and the practical range versus the theoretical. But let's first get a look at what we've got. We've got 150. We know it goes up forever, or it goes up rather, and then changes direction and comes back down. So you're going to be asked a lot of different questions. And the first thing I ask you is to define the theoretical and the practical domain. So let's talk about what that means. The practical domain is the domain that makes sense. It's practical. So we first, in order to determine that, need to know some values. But we are going to end up comparing that to our theoretical. So we've talked about domain before for parabolas, and as you recall, a parabola, if it opens up, it goes up and left forever and up and right forever. If it opens down, it goes down and left forever and down and right forever. So theoretically, we know that the domain of all parabolas should be all reals, which we denote by using interval notation as negative infinity to positive infinity, right? Okay. So the theoretical domain for the function, how do you know this? We're going to say the theoretical domain is from negative infinity to positive infinity. How do we know this? The theoretical domain for all parabolas is all reals, meaning it goes left and right forever. Left and right forever in theory, right? But when we apply quadratic functions in the real world, we don't have a forever in real terms. So if we think about this rocket, while it, if I graph it with both ends, we're going to think, well, yeah, it goes up and down. It's going to go left and right forever, as domain does. But really, we can't have negative time. So if you recall, it says that this function models height as a function of time, which means that our input, or our x, is time, and that belongs on our x-axis. So we have time on our horizontal axis and height on our vertical axis, the y-axis. That's important to understand too. So time, we can't have negative time, so it doesn't even make sense to have points on the graph to the left of the origin here. It also doesn't make sense to have points to the right of when it hits the ground, because that would indicate that the height is negative. And we know that the rocket is going to go up and then hit the ground and stop. So this isn't even relevant. It's not practical. And that's why we use that term practical for practical domain. In practical terms, we only want to pick the x values where the rocket could exist. So it exists at a time of 0 seconds. The initial height before it takes off is 150. But our graph really doesn't make sense past the time that it hits the ground. In this case, the x-axis, meaning we need to find the 0. So we need to know the 0. We already know that at this point, this is the ordered pair 0, 150. So if we think in terms of practical domain, that means it starts at 0 and it ends whenever it hits the ground. Well, that means we need to find in our calculator when it hits the ground, and then label that point on our graph. Remember, to do that, we put y2, put 0 in for y2. We can make our line bold if we want so it shows up on our graph. We also haven't graphed it yet in our calculator, I don't think, and found the max. So to do that, again, remember we go to second graph and we say, well, how high did that rocket go? Well, according to our graph in integer second values, we see that the graph increases until after 2 seconds, and then it starts to decrease. One thing I want you to keep in mind is, again here, it wouldn't even make sense to have the graphs past 7 seconds because we can see the height goes from 30 feet above the ground to negative 102 feet below ground. So we know that it's hitting the ground between 6 and 7 seconds. But because I can see that maximum height based on my table is 238, I'm going to hit window and adjust my Y max to a number higher than 238. So I'm going to adjust it to about 250. So leave some room in there. When we do that and hit graph, we can clearly see the parabola and when it hits the ground, and there goes our bold line to represent the graph of y equals 0. So we want to find the intersection. So second trace 0. Hello? Hey, what's up? I'm trying to finish up so I can get home. I'm recording a video. Let me call you back, okay? Well, that wasn't nice. I'll deal with her when I get home, okay? Oh, that's not nice. I'll deal with it when I get home, okay? I gotta go. All right, bye. Sorry about that. So second trace 5, we want to move our cursor just like we did with problem 1, or 2 rather, where we had to move it over to find the 0 and hit enter, enter, enter. And we can see that the graph is going to hit the x-axis at 6.25 seconds. So at 6.25 seconds, our height is 0. Hopefully that makes sense. So while our theoretical domain is from negative infinity to positive infinity, our practical domain is going to only be from the 0 that makes sense to the other, to the 6.25, the starting x value to the ending x value. So remember, it does include 0 and it does include 6.25, so we are going to use brackets to define our practical domain on the interval from 0 to 6.25 inclusive. Oops, inclusive, should be a bracket there. So then I ask you to explain what that basically says. So that means I would probably say the practical domain includes values, or let's say x values, for which the rocket is, let's say is, well, it's resting at 0. So we could say it's, let's see, the practical domain includes x values for which the rocket is, why don't we say it has a non-negative height. So remember, non-negative means 0 and positive. So that means you can have a height of 0. You just can't be negative. So non-negative, again, means 0 and positives. Okay? So the practical domain includes x values for which the rocket has a non-negative height. Then it asks, what is the height of the rocket 2 seconds after it is launched? Well, whenever we know x, or our input, which is time, of 2, and we need to find that coordinate, the easiest way to do that is to look at our table. So as soon as I go to my table, you can read that the height is 238. So, uh-oh, here goes my kids again. Hello? Hello? I do, but I'm trying to record a video and get out of here, so I'll be home shortly. No, bye. It's too cold. Bye. All right, 238. But remember I said I want all these application problems answered in terms of to demonstrate that you understand it in the form of a statement. So if it says, what is the height 2 seconds after it's launched, I would simply say the height after 2 seconds, or at 2 seconds, I should say, is 238 meters. Is it meters or feet? I'm sorry, feet. The height at 2 seconds is 238 feet. Next, it asks what is the maximum value of the function and what does it mean in context. So we've already reviewed max with problem number 1. So second trace max. So second trace 4. Move this guy out of the way. Second trace 4, and then again I need to move my left bound. Where is it? Right now it's at 8. It looks like it's too far, so I'm going to hit my left arrow to go back. There he is. So I'm going to hit my left bound on the left side of the vertex, mark it. Right bound on the right side of my vertex, mark it by hitting enter, and then hit enter again. And it says my max is 2.38 seconds at a height of 240.25 feet. Okay, so I've got that on my graph now. But of course, you know me, I'm going to want a statement. So I would just translate this here to, in using your points. So I would say, at 2.38 seconds, the rocket reaches a maximum height of 240.25 feet. Or you could say the maximum height is 240.25 feet at 2.38 seconds. Something of that nature, but it should pretty much have the same intent. Then you're asked, when is the rocket 75 feet above the ground? So this time we know our height, but we don't know the when. So that means I'm trying to find x if I know y is 75. Okay? So if I, again, go to my y2 in my calculator, and before I found the intersection with a height of 0, now I want to find it with a height of 75. So I insert 75 from my y2 and hit graph. Again. Okay, notice we have two points of intersection, one outside of the practical domain and one inside the practical domain. I still want you to state both values, but when you answer the question, I want you to use the value that makes sense. So we're going to hit second trace 5. Again, we're just continuing to find points of intersection. Enter, enter, enter. And I see my time is at negative 0.84. So rounding to the hundredths place. Be careful of looking. Negative 0.84 seconds. So I'm going to draw a line right here on my graph and put 75 on it. And then mark that point as negative 0.8475. And I'm going to do the same thing but find it over here in my practical domain. So to find the other point of section, I'm going to have to move my cursor over here to the right. Second trace 5. Move it to the right here. Enter, enter, enter. It's close enough. And we get we'll just say 5.6 seconds. Okay? So 5.6 seconds and 75 feet. Okay? So, of course, again, I'm going to ask you to write a statement. I do want you to indicate what both of your values are. So I would put negative 0.84 and then 5.6, oh, I shouldn't use parentheses, negative 0.84 and 5.6 seconds. But then when you answer the question, when is the rocket 75 feet above the ground, we don't have negative seconds, so that's not going to be practical. So we would say the rocket is 75 feet above the ground at 5.6 seconds, because the 5.6 seconds is within your practical domain. Oops, sorry. Move it over. Rocket 75 feet above the ground at 5.6 seconds. Alright, so next it says when is the rocket 215 feet above the ground. So now I'm going to hit y equals, and same process. Type in 215 at y2 and find a point of intersection. See how many times it hits. Oh, okay, so now this time we see that it actually hits it twice in our practical domain. It hits it on the way up, and then it hits it again on the way down. So again, find those points of intersection. Second, trace 5. Move your cursor to the point where they intersect. Enter, enter, enter. And they intersect at 1.1 second. So I'm going to come up here and put another horizontal line at 215. But now this occurs at 1.1 seconds. And then I want to find my other one. So same process. Second, trace 5. .6 seconds. So now we have our two values. We know it's going to hit 215 at 1.1 and at 3.6. But I want you to explain what's happening as it hits 1.1, what the rocket is doing. In this case, it's increasing in height and then decreasing in height. So I would say the rocket hits 215 feet at 1.1 seconds on the way up. And at 3.6 seconds on the way down. So kind of show me that you understand what the rocket is doing, the path of the rocket there. Alright, so on G, this should actually be, change that D on the end, change that to an E. It says, why are there two answers to part E, but only one practical answer for part E? So if we go back to E, recall both E and F were about finding points of intersection, meaning finding time if given the height. But there was only one that was in the practical. So if you think about why we did not use negative 0.84 in the answer, we only said the rocket is 75 feet above the ground at 5.6, it was because this is negative time, and it is not in the practical domain. So it doesn't even make sense to say that the rocket is 75 feet above the ground at negative 0.84 seconds. It doesn't make sense. So why are there two answers? So we can say that, well, theoretically, meaning in theory, because there were two, we did calculate two, theoretically there are 2 points with height of 75, but only 5.6 seconds was in the practical domain. Or in other words, maybe in parentheses, you cannot have negative time. Cannot have negative time. So theoretically, there are 2 points with a height of 75, but only 5.6 seconds was in the practical domain. You can't have negative time. So then you're asked for h, what are the intercepts of your function, and what do they mean in the context? Well, by intercepts, we're referring to our x-intercept and our y-intercept. So I'm going to circle those, our x-intercept and our y-intercept. So if you think about what this was, that was actually the initial height for our y-intercept. The x-intercept of 6.25 represented the time when the rocket hit the ground. So that's exactly what I would want you to say. What are the intercepts of this function and what do they mean? I would say the y-intercept of 150 means the initial height of the rocket is 150 feet. The y-intercept of 150 means the initial height of the rocket is 150 feet. The x-intercept of, and if you recall what that value was, 6.25, means the rocket hits the ground at 6.25 seconds. Oops, sorry. The x-intercept of 6.25 means the rocket hits the ground at 6.25 seconds. And lastly, almost, I'm going to do theoretical and practical range as well. I covered that in class. Lastly, you are asked, what are the intervals of increase and decrease on the practical domain? And I'm going to grab a highlighter. So remember, your practical domain is only the part where that represents the path of the rocket. Everything else doesn't even matter. But we do know that it increases here. So if I draw an arrow showing that it increases, remember when we state intervals of increase and decrease, we're only defining the x values where that action is taking place. So remember that here, this x value is 0. Here, when it reaches the top, our x value is 2.38. After that, it is decreasing in height. So it decreases until it hits the ground. So we would define the decrease as from 2.38 to 6.25. So all of these values here we're going to use to define our increase and decrease. So I would say increase. Our interval is 0 to 2.38. Remember never to use brackets like you can with domain and range. Intervals will always be with parentheses. And then for decrease, it's decreasing on the interval from 2.38 to our 0 at 6.25. Notice that covers the span of our practical domain from 0 to 6.25. Okay? So what do they mean in the context? Well, basically, it means the rocket is increasing in height up to 2.38 seconds. Then rocket is decreasing in height until 6.25 seconds. And that was a lot, but those are all the applications of functions that you need to understand. Lastly, I'm just going to explain practical and theoretical domain and range. So you didn't have a question on your practice that had theoretical and practical range, but on your test you do. So I want to make sure I cover that. So remember that theoretically, your parabola goes up forever or down forever, depending on whether A is positive or negative. In this case, because our A was negative, it goes down forever. So we would say that the range of this function Remember, range is your lowest y to your highest y. That would mean from negative infinity all the way up to your highest y, which from your max point is 240.25. So for our theoretical range, we're going to say our lowest y is negative infinity. Our highest y is 240.25, inclusive. Our practical range, however, is only the range that makes sense. So if you think about your rocket is not going to have a negative height. The lowest height would be 0. Remember, we want to look at our y's. So our lowest y is 0, our highest y 240.25. So our practical range will include 0 as our lowest and go up to and include 240.25. So remember, to find your theoretical or your practical range, you're going to have to know your max value, but ranges, all your y's, your domain are all possible x's. So theoretically, it goes down forever, but that means we would state our range from negative infinity up to 240.25. Practically, it's only from a height of 0 to 240.25. And that concludes everything you need to understand about the applications for your test.